So we actually are very good now, right? If you can follow what I'm saying. Now, so let's summarize a little bit, and we will go to the matrix. We're done with the scalar, we have done the vector, and it's very close to matrix now. So we want to talk about so-called operator, eigenvector, and eigenvalue, right? So first of all, we know what every state will represent with a vector, right? Every state of the electron, my state or whatever, is a vector in the hyperspace. Now we have operation. I rotate the spin, I do something to it, manipulate it. It is an operation. It will correspond to an operator. If you have taken computer graphics before, probably you did not, but all this game or whatever is nothing but just a matrix multiplication. How do you rotate the object when doing the shooting game? How the scenes change? It will stretch, it will shrink, right? Ours is very simple. We don't stretch the vector, we don't shrink it, because you stretch it, you are going to change the length. That is not physics. We only do rotation. The only problem is rotating not in 3D space, but hyperdimensional space. We cannot see, we cannot feel. Okay? So all the operation is just an operator. So it is also just a matrix to rotate the vector. Now, some matrices are very special. If we apply the matrix to a certain vector, and the result is that it gives us a constant times the vector. For example, A applied to A equals to A times A, right? I hope you can understand what I'm writing here. Here is still not clear. A is the matrix. A matrix multiplied to a vector becomes a number multiplied to that vector. Okay? Then we say that A is the eigenvalue of this matrix A, and then this vector is the eigenvector of this matrix A. If this equation is satisfied, we say this A vector is the eigenvector of this matrix A, and this A number is the eigenvalue of this matrix A. So every matrix has two properties that are important. It has eigenvector. It also has eigenvalue. And what is the relationship between the eigenvector and eigenvalue with this matrix is that you multiply a vector by the A, then you will get its eigenvalue times the eigenvector. Okay, we'll see that later. Maybe now it's confusing. I just give you an overview. Okay, let's take a look at the Polyspin matrix, right? We don't need to go to whatever linear algebra, right? Look at the example, then we will know, right? And this is the matrix you do use a lot. And you trust me, there is something called spin in this world, even you have not studied physics. You can say, it's just like a spinning earth, spinning electron. Fine, you can think in this way. But remember, that is not the real picture. It's just like the color of the something, okay? We call it spin because it has some property resemble the spin, the real spin. You can call it triangle and circle if you like. Tom and Mary is the same. I don't think it gives less information than the spin. But it does have some physical meaning because it corresponds to the classical spin, right? So I call you something a space, called spin, a space. You've never been to that universe, okay? So in this space, we definitely need to talk about the basis vector, right? So in this space, our basis vectors are only two, up and down. It's a two-dimensional space, okay? Two-dimensional Hilbert space. We have not learned Hilbert space, but doesn't matter. As I said, you can call it Tom and Mary. Then what's the problem if I call it up and 0 and 1? Okay, you cannot complain, right? I can also then say that these are the two bases in the column form. Is that okay? For the second one, you basically say I have 0 component of 0 or spin up, and I have 1 component of 1 or spin down. Right? Of course, spin down equal to spin down, right? Just like 1 spin up equals to 1 spin up plus 0 spin down. Is this okay? Yeah? Okay. Now, then I tell you, there is some matrix very useful called a Pauli matrix. And now I give you one of them, right? We don't explain everything. Eventually you understand, we just keep practicing. I give you something called Polyspin Matrix. You just take it for granted. One of them, sigma, this is sigma in Greek alphabet, sigma z equal to 1, 0, 0, negative 1. Just like an identity matrix. So easy, 2 by 2. Okay? Now, let's look at this. If I apply the Polyspin matrix to spin up, what will you be? Do the substitution. 1, 0, 0, negative 1. What is spin up in matrix form? Can you see it clearly? 1, 0. Spin up is the first one. Okay? Let's do the matrix multiplication. 1 times 1 plus 0 times 0. 0 times 1 plus negative 1 times 0. Right? If you forgot, this is the prerequisite of this class. How do you do it? Row times column. 1 times 1 plus 0 times 0 becomes the first element. 0 times 1 plus negative 1 times 0 becomes the second element. Right? I need you to go back to make sure that you don't make mistake. What is this? 1, 0. Which means it is 1 times up. Do you see that? Sigma z applied to spin up equals to 1 times spin up. Again, what is sigma z? Matrix? Vector? What is 1? Yes, eigenvalue, scalar, right? So I apply a matrix to a vector, I get a scalar times the vector itself. So therefore, this is the eigenvector of C, of sigma z. And this is the eigenvalue of sigma z, corresponding to that eigenvector. Now, do I explain now what is eigenvector and eigenvalue? And if you try this sigma z times spin down, you see that this is equal to negative 1 spin down. You have to do it at home. Do the same thing. All you need to do is just change it to 0, 1. Okay? Time's up. I will just stop here, I guess. And okay. So last time we talked about the sigma C matrix, right? If you still remember, the Pauli sigma C matrix is like this. Sigma C equals to 1, 0, 0, negative 1. I will try to memorize this because it is very useful. And particularly, we say that the state 0, 1 and 1, 0 are its eigenvalues. I mean vectors. Right. For example, if I apply sigma z, which I did not show last time, on 1, it is equals to 1, 0, 0, negative 1. Again, 1 is the second basis state, so it's written as 0, 1, right?
if we now do a multiplication, this becomes 1 times 0 plus 0 times 1, 0 times 0 plus negative 1 times 1. What is this? Well, the top is 0, the bottom is negative 1, which is equals to negative 1 times 0, 1. That means this is equals to negative 1 times 1, right? So its eigenvalue is negative 1. That is what we learned in the last slide, right? Now let's look at another matrix. This is called sigma x, right? We did not really say what it is yet, but it corresponds to a magnetic field in the x direction. So this is another spin matrix. Let's see if spin up, which is this one, or spin down, which is 1, are its eigenvector. How do we check it? Very easy. Just apply the matrix to spin up, which is just equal to 0 if you want, right? And sigma x is defined as 0, 1, 1, 0. Again, I advise you to memorize this, okay? It's off diagonal. Later you find out that this is the so-called NOT gate, okay? So for this sigma x, if I apply it to 0 or apply it to spin up, again, what is spin up? Spin up is the first eigenvector, so it is 1, 0, right? So if I do this, when I apply it, it is 0, 1, 1, 0, which is sigma x times 1, 0. Let me do the math again. 0 times 1 plus 1 times 0, right? Because I multiply this row with this column, use the regular matrix multiplication rule. Bottom is 1 times 1 plus 0 times 0. What is this? 0, 1, which is spin down. Isn't that is something like the NOT gate? Because this is 1, right? By applying the sigma x to 0, which is spin up, I get 1, which is spin down. Just like a classical computer, I negate the basis state. Okay, so I challenge you to do an exercise. Try sigma spin down. It should give you spin up. Or in other words, sigma x 1 is equal to 0. As a result, we say that sigma x is a NOT gate. We will study more later, but I hope that first now you have an idea on the importance of the Pauli matrix. Okay? Now, naturally, you may ask, how about sigma y? We'll talk about that later, right? But before that, let's learn how to find the eigenvalues and eigenvector. Just now, I only proved that what is eigenvector, whether a vector is the eigenvector of a matrix, right? Again, what is the eigenvector and eigenvalue? It means that if I have matrix A times a vector A, if you give me equals to a real number A times the vector itself, then we say that A is the vector, the eigenvector of A, capital A. I said many times, you need to be very careful about what you are doing. Capital A is the matrix. This A is the vector. Matrix times vector is what? It is a vector. Small a, this A is a number. Number times a vector is what? Is a vector. That's why left equal to right. Okay? So let's try to find the eigenvalue of sigma x. We just showed that spin up and spin down is not the eigenvector of sigma x. Then what is the eigenvector of sigma x? Let's try to find it. So I will first set up an equation sigma x. This is just like A, right? It's a matrix. I assume that its eigenvector is called V. This just like this small a. And I assume its eigenvalue is C. So when you multiply the matrix A on the vector V, eigenvector, you will get the eigenvalue times the matrix, right? In general, what is V? Well, it must be a linear combination of 0 and 1, right? Which is A times 0 plus B times 1. And that's why I write in this column form, because it means I have A units of first basis vector, B units of second basis vector. Now, which basis we are talking about? We're talking about the basis formed by the 0 and 1 basis vector. And it happened that 0 and 1 are the eigenvector of sigma c. So this basis is also formed by the eigenvector of sigma c. Okay? Anyway, now I can try to find it because A and B can be any number, complex number. Then sigma x times AB equals to 0, 1, 1, 0. This is given, right? Times A equals to a number times AB. So what is this? You do a multiplication, it becomes AB, right? Because 0 times A plus 1 times B equal to B. 1 times A plus 0 times B equal to A. The left-hand side is BA, and the right-hand side just a regular multiplication. It is CA times CB. Now, if these two vectors are the same, their components need to be same, right? This basically saying that on the left, this vector has B components of which vector? Of 0. It has A components of 1. On the right, this vector has CA components of 0. On the right, it has CB components of 1, right? I think it doesn't hurt to remind you again, this is super important. You need to understand what it means. Now, with this, then it means they have to be same. Then it means B must be equal to CA and A must be equal to CB. Okay, so you need to solve this system of equation, right? Now, you can try to, for example, do division, divide these two equations, B divided by A, then equals to A divided by B. Then you have B squared equals to A squared. And what does it mean? It means B equals to plus minus A. Okay, so there are many solutions actually. You can have many complex numbers, but one possible set of solution is you can see that I can set A equal to 1 and then B equal to 1. This is one set. So the eigenvector is 1, 1. Okay? Another possible set of solution is A equal to 1 and B equal to -1. This adjusts the equation. This is the first one is A equal to B case. The second one is A equals to -B case. Right? Then I will get 1, -1. Okay? But actually, this is not good enough. What is the length of this vector? I have 1, 1. The length is square root 2. Then it is not unit vector. So actually, I did not choose a good one. Right? What I need to choose? Actually, I should choose something normalize the vector. Okay, so indeed I need to do is actually choose A equals to 1 over square root 2, b equals to 1 over square root 2. Then my first eigenvector v0 is going to be equals to 1 over square root 2 times 1, 1. And I will choose a equal to 1 over square root 2 and b equal to negative 1 over square root 2. Then I get my second vector v1 equals to 1 over square root 2, 1 minus 1. Is that okay? Yeah. So you can choose many value to satisfy b equal to plus minus a. For example, b can be 100, a can be plus minus 100. But because we need to have a normalized vector, you will choose something so that the unit length, the length of the vector is 1. Try it. What is the components of the 0? It is 1 over square root 2. The component of the 1 basis vector is 1 over square root 2. So the square of the coefficient becomes 1 over 2 plus 1 over 2, which is 1. And this is the correct answer. We normalize it. Okay? So that is how you find the eigenvector. And of course, if I want to find the eigenvalue, then what I need to do is substitute them, right? For example, if I look at v0, which is 1 over square root 2, 1, 1, then I substitute it into the equation. I have 0, 1, 1, 0 times 1 over square root 2, 1, 1 equals to c times 1 over square root 2, 1, 1. Sorry for the writing. 1 over square root 2, 1, 1. Okay, then you try to do a multiplication. You see on the left hand side is the 1 over square root 2 got cancelled. On the left hand side, you get 1, 1 still. Use matrix multiplication. On the right hand side, it is C, right? So it means the eigenvalue is C equal to 1. So the eigenvalue of the first vector, eigenvector, is 1. And similarly, okay, I want you to do it yourself. Similarly, the eigenvalue, when for v1, the eigenvalue is negative 1. Okay, so basically here you tell us that, well, if I have the Polyspin matrix in the x direction, or the x Polyspin matrix sigma z, its eigenvalue is going to be still plus and minus 1. But its eigenvector are different from the eigenvector of sigma z. Now, do you recall some similarity between them, between what we learned earlier in the 2D fake basis? At that time, we have 0, 1 as the basis, and then we have a 45 degree, right? Look, let me draw it again. We have this fake plane, right? 0, 1, and then we also have this fake another basis, right? Plus and minus. Now, do you see that the eigenvector v1 here actually is the same as the plus? v0, sorry, right? So if we treat the eigenvector of the sigma z as 0 here, and 0 and 1, then the eigenvector of x turn out to be just the plus in the fake example I showed you earlier. And the second eigenvector of sigma x is just equals to minus, because it is 1 minus 1, Remember what's 1 minus 1? It's 1, 0, minus 1, 1, right? So accidentally, the fake example we use actually give the same result as the Polyspin matrix sigma z and sigma x. Okay. Anyway, this slide is to help you to review how to find the eigenvector and eigenvalues of a given matrix, and we use sigma x as an example. Okay. So what is sigma x? Sigma x is the operator corresponding to the magnetic field in the x direction. Sigma z is the operator corresponding to the magnetic field in the z direction. So similarly, we should also have the magnetic field corresponds to the y direction in our real 3D space, and we call it sigma y. And this matrix is 0, negative I, 0. And remember, I is square root negative 1, which is the imaginary number. Now, you should be able to find the eigenvalue of sigma y by using the approach I show you here. All you need to do is just to do the substitution by assuming it has an eigenvector called v and its eigenvalue is c. Solve the system of linear equation, then we'll be able to find out what are the eigenvalue and eigenvectors. Okay, so I will not continue here. Now we talk about the spin matrix, and this is something, to be frank, can be very confusing. What is a spin? We always try to associate it with the three-dimensional space. But as I told you many times, the spin is a space of how many dimensions? 2D, right? The spin is a 2D space, except that it has the complex coefficient. Unlike the 2D space on my table, right? It has complex coefficient. So any state in this spin space, it is must equal to A times 0 plus B times 1. It only have two basis states. That's why it is 2D. So how it is related to the 3D? That is because the way we measure the spin is through the energy. So under magnetic field, different spins have different energy. Okay, so for example, if this is an energy scale E, okay, so when there is no magnetic field, B equal to 0, whether you are spin up or spin down, they are the same. You cannot distinguish them, right? How do you know something is spin up? You need to do some experiment and then see whether it emits a photon or it absorbs a photon, and then you know whether it's spin up or spin down. Now, if there's no magnetic field, they are degenerates. What we call is degenerates. The two states have the same energy. You cannot distinguish them. So how can we distinguish them? If now I apply a magnetic field, for example, apply the magnetic field in the z direction. Now, this is a real 3D space. I'm talking about the z direction. In this case, the spin down, or maybe we call it 1, okay, it's going to have a high energy. Now, here I call this positive charge. It's not electron, right? You may see something opposite where you play with electron. But let's just follow this approach. That is because when your spin is in the same direction as when the magnetic moment is in the same direction as the electric field, you get lower energy. This is just physics. Please trust me. You don't need to go so deep, right? And because it's positive charge, the spin and the magnetic moment are in the same direction. So in summary, you just trust me. When it is positive charge, the spin that has the same direction as the magnetic field is going to have a lower energy. And we call this state 0. The one that has higher energy, we call it 1. Okay? And that is why we say that the eigenstates they are vectors, right? We already say that. But the spin has no relationship or direct relationship to the 3D space. Okay, I try to emphasize this spin is not really saying that I have a spin pointing up. It's just that the spin states create a magnetic moment that is pointing up. Okay, it is not really a 3D vector. So as a result, we call it sigma c. It's just because this is the two possible states when you can find when the magnetic field is in the z direction. Right. Similarly, if this is the energy, if I try to have the spin right and spin left, when there is no magnetic field, I cannot distinguish that. But if I apply a magnetic field in the x direction, right? Then the one that goes in the opposite direction is going to have a larger magnetic field, larger energy. And the one that goes in the same direction of the magnetic field has a lower energy. Okay, so again, it doesn't mean that the spin direction is not really a 3D direction. And the reason we associate this to the sigma x is because we're doing the measurement, we are measuring the x direction. Okay, so one thing that can make us very confusing is that we already know that spin up equals to 0 equals to 1 over square root 2 plus negative, right? If you try to plug in, you will find that it is like this, right? But it is definitely not equals to, you cannot say that plus is x hat, and then this one plus negative x hat. Can we say that? No, because plus and minus are not really the in 3D space that my spin is pointing to the left and pointing to the right. Because if that is really the case, the basis vector is really pointing to the left and right, then they will just cancel. But no, they are not cancelled, right? They become 0. That is because the spins live in a space that we cannot see. It has nothing to do with the 3D space. It has an indirect relationship because when we apply magnetic field in our 3D space, their basis state has this certain property. So for different magnetic field direction, we have different basis vector for this spin space. Okay? Now, so we have learned the Pauli matrix. Now I would like to show you some properties of the Polyspin matrix. So let me remind you again, what are the Pauli matrix? X equals to, can you remember? 0, 1, 1, 0. Sigma y equals to 0, negative 1, negative I, 0. How about z? This is the easiest. 1, 0, 0, negative 1. This is diagonal. Now I want to introduce another matrix. What is this? This is just the identity matrix. It means that it's just like the 1 in our multiplication. You multiply this matrix to any vector, it returns the same vector. Okay? So usually, Pauli matrix are only talking about these 3 matrices, but very often this I has some special property that is very similar to them, and you can group them together to form a larger set. Okay? Let's see, we are going to look into this later. But what are the properties of this matrix? The first property is that sigma x squared equal to sigma y squared equal to sigma z squared equal to I squared equals to 1, 0, 0, 1, which is I. So if you apply the Polyspin matrix of the same kind 2 times, you actually go back to the original place. It becomes an identity matrix. Let's check, for example, what is sigma x squared? Well, 0, 1, 1, 0 times 0, 1, 1, 0, right? And by definition of matrix multiplication, it is 0 times 0 plus 1 times 1. And then the second row, sorry, I say the wrong thing, right? This is the first 0 times 0, 1 times 1 becomes the first element. Then we will do this row times this column, which is 0 times 1 plus 1 times 0. That becomes the second element, right? Then we continue, right? This one, it is 1 times 0 plus 0 times 1 for this one. This is 1, right? And then the last one is this row, right? Second row and the second column multiplied together becomes the second row and second column element. This is 1 times 1 plus 0 times 0. What is this? Well, the first one is 1, the second one is 0, and then 0 and then 1. What is this? Identity. Indeed, the sigma x squared give you I, identity matrix. Okay. The second property I want to talk, so I want you to memorize this. Okay. The second property I want to talk about is the so-called anti-commutation. Anti-commutation. So what does it mean? This is property sigma I sigma j equals to sigma I sigma j plus sigma j sigma I, and it equals to 2I delta ij. This is the anti-commutation rule. Now, looks very long, but it's very easy to understand. First, this is just nothing but a definition. Sigma ij with this curly brace, it means sigma I times j plus sigma j times sigma I. It's just like 1, 2 becomes 1 times 2, 2 times 1. That is just the definition. That is called anti-commutator. Okay? What is the result? The result is 2 delta ij, 2I delta ij. Remember what is delta ij? We learned it earlier, right? This is the Kronecker delta, which means it is equal to 0 if I equals to not equal to j. It's equal to 1 if I equal to j. We learned this when we're doing the orthonormal property, but it doesn't need to be vector. This is just a number, right? Delta ij. So what does it mean? For example, It's basically saying that if I and j are the same, they are the same sigma x or sigma y, they are the same, then I'm going to get 1, it gives me 2i, which makes sense, right? I will show you. For example, if I equals to x, j equals to x, then of course I equal to j. So as a result, it means that sigma x equals to sigma x plus sigma x because I equal to j, right? It tells us that this equals to 2i delta xx, but xx is just the same. I equal to j, so this is I, which is 2i. Is it correct? It is, because we just told you that sigma x squared means sigma x times sigma x should give me I, right? So I have 2 sigma x, so I have 2i. So this equation is correct from here, right? Okay. Now, what if they are not the same? Another example, right? So this is not related. When I equal to x, j, let's say, equal to y, for example. When I equal to x, j equal to y, then what do we have? Sigma x, sigma y equals to sigma x, sigma y plus sigma y, sigma x. And what is the result? I need to do calculations, right? So this is equals to, what is sigma x? It is 0, 1, 1, 0. What is sigma y? 0, negative I, 0, right? Just look at the top. And then 0, negative I, 0 for sigma y. And then 0, 1, 1, 0. Okay? Do some calculation. You will find that this equals to 0, which is just equals to delta ij, right? For those who are not familiar with this, let me really try to do a quick calculation, right? On the top, 0, 1, 1, 0, the first term, instead of rewriting, maybe I just it directly. The first term, 0, 1, right? 0 times 0 plus 1 times I. This gives me the first term, first row, first column. And then we have 0 times negative I, right? Plus 1 times 0. And then we have 1 times 0 plus 0 times I. And then we have 0 times negative I. I'm sorry, 1 times negative I plus 0 times 0, right? What is this for the first term? Yeah, this is I, 0, 0, negative I. Okay, so this is the first term. Now, if you look at the another part, right? Now, I'm not going to do this expansion. So it clearly, right, I will see that 0 has no effect. So I have a negative I for the first term. And then I have 0 for the second term. And then I have 0 for here. And then I have I again, right? And if you add them together, you get 0, 0, 0, 0, right? Which is equal to delta x, y, which is 0 times I, right? Okay? Maybe too long, but in summary, these are two important properties of the Polyspin matrix. I hope you can memorize. Their square is equal to I, and they have the anti-commutation rule. Means that if you swap them and add them, you will get 0. Okay? Otherwise, you get 2i's. Okay, so let's summarize what we have learned so far, right? we say that we actually start from almost nothing, and now we were able to understand there's something called Pauli matrix. Also, it's just given by the mathematician or the physicist. And we know how to find the eigenvector, eigenvalue, and we know their properties. Now, why don't we even dive deeper to play with this Pauli matrix to enhance our understanding of the vector space? So far, our vector space is always like a vector, and then you do a linear combination. Now, let's take a look at this description, right, about Pauli matrix from Wiki. It says that each Pauli matrix is Hermitian. We will ignore now. We will learn it very soon. What is a Hermitian matrix? Okay, ignore it now. But you say that the Pauli matrix together with the identity matrix, remember I just mentioned to you, they sometimes call it sigma 0. Okay, they sometimes call it sigma 0. So just now I told you that we have 4 matrices, right? Sigma x, sigma y, sigma z, and then I. Now I decided to call it as sigma x, sigma y, sigma z, and sigma 0. It doesn't matter. It is just a symbol, right? Which is 1, 0, 0, 1. It say that it forms the basis of the real vector space of 2 by 2 Hermitian matrix. What does it mean? Basically, it is saying that any Hermitian matrix, we have not learned that, right? But it's just saying that any matrix A, B, C, D with this A, B, C, D being the real, being Hermitian, they have the Hermitian property, okay? Which means that, I just tell you now, later you will realize that it is just like saying that A, B, B star, D. All the matrix has this form, okay? You will learn that later. Maybe I should just erase this one. Any Hermitian matrix can be, 2 by 2 Hermitian matrix can be represented by A, B, B star, and D. So we have 3 numbers. Any of them is a linear combination, alpha of sigma plus beta of sigma y plus gamma of sigma z plus delta of sigma 0. It means it is equal to alpha times 0, 1, 1, 0 plus beta times 0, negative I 0 plus gamma times 1, 0, 0, negative 1 plus delta times 1, 0, 0, 1. Now, do you see that this is very interesting? The basis doesn't need to be a vector. It can be a matrix itself. And then all the elements in this vector space, still a vector space, is actually a matrix itself. All this matrix can be decomposed as the linear combination of these 4 matrices. So what is the dimension of this space? It is 4D because I have 4 basis vector. Okay? I try to think about this when you see if you can understand. You don't need to know what is Hermitian at this point, right? We just say that, okay, this space or this matrix is a linear combination of these 4 matrices, and they are just the basis state. Just like the 0 and 1 in our 1 qubit state, here you have this, right? This is not directly related to our qubit, but it's used in quantum mechanics. But I just want you to appreciate what a vector space can be. Now you see that as long as you follow the definition, vector space can be very interesting, right? We'll see another even more interesting example in the next slide. But at this stage, I would like to ask you, whenever I write the basis state, or whenever I write the vector, whenever I write the matrix or the vector, I need to choose a base to write, right? A basis to write on that, right? What basis we are using when I write this? it turned out we are still using the sigma z basis vector or basis. Okay, the basis formed by 0 and 1. Okay, and that is because you see the sigma c now is written as 1, 0, 0, negative 1. If you find its eigenvalue, you find that it is exactly just 0, 1. So the eigenvalue is indeed the basis that we are writing. Okay, maybe not that clear to you now, but as we do more, you will understand better. But always ask yourself which basis you are using, and also ask yourself what are the meaning of each symbol. Alpha, beta, gamma, delta are just the numbers, a scalar. These are the matrix, so they add together becomes a matrix. Okay? Now, we say that the Pauli matrix is referring to a special direction of magnetic field, right? Sigma z, then I have a Pauli matrix of a kind. If the magnetic field is in the x direction, is 0, 1, 1, 0. What if I have an arbitrary direction? What we are saying is this. We have this 3D space. Z, X, and Y. Okay? Now, just now we say that if the magnetic field is applied in the Z direction, for example here, then the corresponding operator is sigma z equals to 1, 0, 0, negative 1. If the magnetic field is in the x direction, the corresponding operator is 0, 1, 1, 0. And if it is in the y direction, then the corresponding, this is the magnetic field. Right. And if it is in the y direction, the corresponding operator is 0, negative I, 0. Okay, what if my magnetic field is in an arbitrary direction, n, a unit vector, arbitrary direction? What would that be? Okay, now, for any n, it must be now this is very interesting. We're doing 3D space now, right? I'm seeing the magnetic field, right? So it must be in a certain direction, which is a linear combination of x hat plus y hat plus z hat. Yeah? So it has this component, nx, ny, nz. If you like, you can write it as nx, ny, and z. This is what you have learned before in a 3D space, right? In a 3D space, that is the equation. And again, you ask yourself, what is the meaning of nx? It means I have nx components of x hat. What's the meaning of ny? I have n component of y hat. What's nz? You have nz component of xz. This is a unit vector in the real 3D space. Okay? But it also means that the magnetic field, now I apply a magnetic field pointing in this direction, right? I find a magnetic field pointing in this direction. What is the Polyspin matrix corresponding to this? Okay? The Polyspin matrix corresponding to this is actually a spin vector. And let's look at this. This is very interesting. It is equal to n dot, sorry, not Polyspin vector. I should say, I say something wrong. Polyspin vector is defined as sigma vector. And what is sigma vector? Sigma vector equals to sigma x, x hat, plus sigma y, y hat, plus sigma z, z hat. I hope you won't get confused, won't feel this is weird now. What are the bases of this vector? X, Y, Z. The real space, X, Y, Z. What are the coefficients of the bases? They are matrix. Okay, so in the past we used to have real number as the coefficient in our 3D space or 2D space. Fine. Then we started quantum computing. We say you can have the complex number as the coefficient, right? You have an alpha times 0 plus beta times I. Now you can even have a space that has the matrix as the coefficient. But that is nothing strange to you now, right? Because as long as we follow all the rules, we know that in every space, this space is not really the space we live in. It's a mathematical space. In that space, we always have some basis vector. This basis vector can be just a vector like x, y, z in our real 3D. It can be 0 and 1 plus minus that we cannot see in the qubit. Or it can be also like what we just said, the matrix itself is a basis, right? Same for coefficient. It can be real, can be complex like the qubit, or it even can be a matrix. Okay, so very interesting, right? So I hope that now it opened your mind. You can accept this weird concept. But the point is, you can map all this due to the linear combination of the basis, right? I still call them basis vector. And the coefficient can be real, complex, or matrix, or whatever, as long as you follow the rule of the space. Okay? If this is the case, what is the Pauli, the matrix? The spin matrix corresponds to, and this is definition, okay? We define spin vector as this. Corresponds to a B field in n direction, means that it's pointing here, is sigma n dot sigma vector. Okay? What is n? It is nx, ny, nz, right? But because we're doing the inner product, I need to do a transpose. And then what is sigma vector? It is what I have here, but it is nothing but this. Sigma x, sigma y, sigma z. Okay? So this is equal to nx, ny, nz after transpose. This, if I really want to write it out, it is 0, 1, 1, 0, 0, negative I, 0, 1, 0, 0, negative I. And then you do multiplication, which is nx times 0, 1, 1, 0, ny plus ny times 0, negative I, 0, plus nz times 1, 0, 0, negative 1. What do you get? nz, nx minus I, ny, nx plus I, ny, nz, negative nz. Okay? So this is the matrix correspond to the magnetic field pointing in the n direction. Now here I try to use the procedure we have learned before. But if you remember how to do a dot product of two real space vector, you should remember that it is just the x component times the x component plus the y component of the first one times the y component of the second one, right? Remember this? For example, a dot b, right, is just equal to ax bx plus ay by plus az bc. If you remember this for 3D, right, for the 3D part. Right? Okay. The most instructive thing in this slide is to tell you that the basis can be very weird, the coefficient can be very weird. That doesn't matter. If you understand this, there's no problem in understanding the qubit because it is much easier. Now let's check if we are doing the right thing, okay? Just make an example. For example, what if the n, right? We say the B is pointing in the n direction. What if the n is just equal to y, right? We just point at the y direction, right? The n is at y. Then what is the matrix? Then we have n dot sigma equals to, because it points at y direction, then you have nx equal to nz equal to 0, right? Because you don't have that component. Ny equals to 1. Sorry, this is not clear. Let me rewrite it. Right? You have nc equal to 0, right? So as a result, you have what? Based on this equation, on this one. nc is 0, nx is 0, ny is 1. So you have negative I, 0 plus I, and then negative. Here you have negative 0. So this is what? 0, negative I, 0, which gives you sigma y, right? So sigma y, sigma z, sigma x are the special case of this generalized spin operator in arbitrary dimension. Okay, so I think we should take a break from this spin operator.